it has started.
Great.
Then how about we start now? So I think we will proceed like this. I will first briefly introduce you to the audience, and then you can start your talk. I may interrupt you if you feel okay. Then I may interrupt you with the questions from the audience.
I love getting questions interactively. It's much more fun for me to, give a talk that's tailored to what you guys are interested in. So please feel free to ask questions along the way.
Yeah, sounds good. So the audience is in Tencent VOOV meeting. So you can feel free to unmute yourself and interrupt with your questions. For the audiences from Bilibili or WeChat, so I may collect your questions and interrupt Professor Udell during her talk. We will also have a Q&A session after her talk, which may be roughly after 15 minutes. And then we will also record this meeting, and you may find the recordings later. So, okay, so let's start. It's our great honor to have Professor Udell, who is from Stanford Management Science and Engineering, to introduce her recent work about the application of large language models in mathematical programming, mathematical optimization. So let's now enjoy Professor Udell's talk.
Okay, well, it's great to be here. It's great to be able to chat with you all. I have a setup where, for those of you who are on VOV meeting, I can see your cameras if you turn them on. And I'd love it if I could see a couple of your faces. So if you're willing to turn on your camera, that would be wonderful. So I can make sure that you understand when you're nodding, and when you're confused, you can shake your head and I'll know to slow down. Okay. So I'm here to talk to you about AI and the future of optimization. What does it mean for optimization? As far as I can see, that we had these incredible advances in AI, especially in large language models. By the way, I'm also getting over a terrible cold, so my voice sounds very hoarse, but I hope you'll bear with me. Okay.
Yes, sounds good.
This work is led by two fantastic PhD students who are working with me at Stanford, Alia Madi-Tashnizi and Wenzi Gao, who I believe is in this meeting. Okay, so here's the challenge. Optimization is important in so many sectors of the economy. Anywhere that people can make their processes more efficient, it's useful to use optimization to make the processes more efficient. I often like to say optimization should be able to make anything 15% faster, 15% cheaper. 15% is a parameter. Maybe for some problems it's more, for some problems it's less. But there's often a lot that you're leaving on the table if you're not solving your problem with optimization and a proper solution method. And this is true in domains from energy, maybe designing the smart grid, where we're deciding how much power to produce in order to meet demand, or deciding how to shift demand in order to adapt to the production of a renewable grid with solar and wind energy. It might be in routing problems. Maybe we're deciding how delivery trucks should go from house to house in order to drop off packages and groceries and food. And we want to make sure that they're taking the easiest routes to save driver time and to save costs on gas and fuel. Okay. In supply chain, we want to be able to deliver the products to the customers where and when they need them. And there's a cost to holding products on the shelves. There's a cost to having a sort of extra staff when you don't need them, right? So you need to figure out how to sort of optimally allocate your supply chain so you don't run out of products where consumers need them, but still run an efficient business. Right. And then scheduling, right? When you're trying to schedule airlines to move between cities, there are lots of optimization challenges, especially under sort of dynamically changing problems where new constraints are arising all the time. Suddenly something happens, many of the airplanes are grounded, maybe there's a strike and many of the workers won't work. And you need to figure out how to adapt to these changing demands, right? So there's constantly sort of new optimization problems that are being developed in sort of new settings in which they could be applied. And these are only the largest scale settings, right? Part of the reason why sort of applications of optimization in industry do tend to focus on these extremely large scale settings is that the impact of optimization, if it's going to be a percentage of the current allocation, is going to be larger if it's a bigger problem. And so if you need the 15% or whatever the fraction is that you're going to save on the cost to be greater than the salary that you're going to pay to someone to actually set up and formalize your optimization problem. Okay, so I think that means that there's a lot of places in our economy where optimization could be used and should be used, right, in order to, have a more productive economy, in order to minimize global warming, and it's not being used because of the difficulties of optimization modeling. And I think this is an important point, especially for people who are used to academic side of optimization, because in academia, we often spend a lot of time thinking about what algorithm we're going to use to solve the problem, or designing better algorithms to solve a given problem class, algorithms for mixed integer linear programming, algorithms for linear programming, first order algorithms, second order algorithms, algorithms for convex programming, smooth, non-smooth. But in applied optimization, the bottleneck is often modeling, figuring out how to set up your problem, how to get access to the data. Okay, so we started wondering when we saw the amazing things that new large language models are able to do, what this would mean for optimization and whether we could speed up and improve optimization modeling. Okay, and in this talk, I'm going to focus on mixed integer linear programming because it's by far the most well-studied and probably the most widely applied throughout sort of broad sectors of the economy of any optimization framework. So let me give you an example problem. This is an example problem that comes from pricing. This is from a real retailer, one of the top fashion retailers in the globe. And this is the kind of way that a business person might be able to write down a problem. They might be able to say, look, we're selling clothing in several markets. We can estimate how price changes affect sales for each article. We know that price changes, they have to be in multiples of €1 because we want the prices to be simple, listed on the price tags. The initial prices are given. Every article has a maximum production volume. And given the sales forecast and the past elasticities, we want to choose new prices to maximize our expected revenue, right? This is something you can imagine a business person writing down. You cannot imagine a business person writing down the Garobi model that corresponds to that problem. So this is the Garobi model. And you can see, actually, if you look through it, it's not very complicated code, but it's certainly beyond the capability of most business managers. Okay, so this is something you'd have to call in an optimization expert to write. Okay, so we're wondering what fraction of an optimization expert's job can we automate away using large language models? Okay, I guess the idea is that you could go from the problem to the mathematical formulation all the way to code to solve the problem by automating it using large language models. So we have to think a little bit more carefully about what tasks are involved in optimization modeling. Okay, first step is understanding business logic and natural language. Here, if I think I probably shouldn't click through to it. If I share my slides with you later, this is a 60-page long description of a single grid optimization problem. And it has tables of parameters that go on for many of those 60 pages. Okay, so these are extremely complicated. Certainly, they're beyond the ability of one human mind to remember the whole thing. This is actually a great reason why we might expect computers to be better and helpful in being sort of assistants for optimization modeling, is that sometimes these problems are very large and challenging. The second step is mathematical reasoning, figuring out how to transform the business logic given into a mathematical form that matches a template for which there is a solver. Like transforming it to, for example, a mixed integral linear program or maybe a disciplined convex program. And the third step is implementing solver code to map your problem data onto that problem class, onto that solver. So we want to know, can a large language model like ChatGPT help? Okay, so the first approach, the first thing you might try is just to ask ChatGPT. Let's see what it does, right? The advantage of that is that it's easy. On the other hand, it's very unreliable. Okay, you can't be sure that the code that it gives you works. In fact, oftentimes the code doesn't even run, it just produces an error. The second problem that's pretty clear is that it's not scalable. Okay, and that's in two senses. Number one, here I've sort of put all the numbers involved to specify the problem in the prompt. Okay, now we know that, while statistical learning-based methods may be good at filling in the next word prediction, they're not going to be good at filling in the next number prediction. They can't do math well. So giving all the numbers to the large language model is a recipe for disaster. Okay, we want to make sure that the numbers get given to the model. And we don't want the length of the prompt to increase with the size of the problem, because some of these data matrices can have billions or even trillions of entries. Okay, we don't want to have to put that in our prompt and confuse the large language model. Okay. The other notion of scalability we might care about is the length of the description. Like, for example, that energy systems example that has 3 pages of parameters just in one table. Okay, you might not want to you might be worried that as you add more of these parameters to one LLM's context window, you might overload the LLM and you might start to forget about these constraints. And this is a phenomenon that we see. Any questions so far?
So Professor Udell, so you have tried running this in ChatGPT, and so sometimes it works and sometimes it fails, right?
Mm-hmm.
If I understand that correctly.
Yes.
So like in what situations it would fail more likely? I remember you just mentioned like if you have some specific numbers, it will more likely.
So it fails more. It fails more for larger problems. It fails more for more complex problems. It fails when there's sort of subtle things about the modeling. It sometimes fails because it just like forgets things about how to write code. So it will just it'll use a variable it hasn't defined, for example. So it doesn't, there's no error checks to make sure that your code even, compiles, right? So
sometimes we may need to debug, right?
That's right. So it can fail for subtle reasons or for really obvious reasons.
Got it.
Okay. So let's think about this more broadly. Unreliability is a problem for large language models in many domains, right? Not just in optimization. It's a problem when you're writing code, doing sort of code completion. It's a problem for information retrieval and summarization. And it's a problem if you're using large language models to try to develop new mathematics, for example, to prove new theorems. Okay. It's a problem in all of these domains, but they're very different in one key attribute. And I want to sort of highlight this, which is, can the output be reliably checked? And at what cost? Can it be checked by traditional code? That's very cheap. Can it be checked by a large language model? That's also quite cheap. Or does it need to be checked by a human? That's a little bit more expensive. And yet still, if we can have the LLM develop code that's checked by the human and use less human time by having them work with the LLM, that's still a major advantage. Okay, so our hope is to design a way for AI to work with humans and to exploit the unique attributes of optimization to reduce errors. So let's think about the challenges that our large language model will experience in solving real-world optimization problems. One is ambiguous representations. For example, the same problem might interchangeably use the words portfolio or allocation. Another problem is long problem descriptions, like the 60-page power plant example. A third problem is large data matrices, right? Just a lot of numbers might appear in your optimization problem. And a fourth problem is unreliable outputs and hallucination. Okay? the LLM may produce things that, don't make sense and are easy to identify, or that don't make sense and are so similar to what you meant or to what you might have meant that they can be hard to identify. Okay. So they can also introduce really subtle errors, right? Like the code runs, the result is incorrect. Sometimes some constraints are ignored, or they're changed to match more common constraints, or a variable might not match its desired interpretation. For example, a variable called abs price might not actually be constrained so that it's equal to the absolute value of the price. Okay. So our goal here was to design an architecture, a way for LLMs to work with each other and to work with humans in order to reduce the likelihood of these errors. So here's the structure that I'm going to sort of explain to you our current implementation of a system that we call OptiMUS, which stands for Optimization Modeling Using Solvers. So we start with a problem description and a table of data. Okay. We pre-process the description into an initial state that I'll describe on the next slide. From that initial state, a team of LLM-powered agents work together to solve the problem. The manager agent looks at the state of the problem and sort of the messages that it's received, and it decides which of these agents to give the problem to next. Usually the first one that it calls is the formulator. The formulator takes the natural language description of the problem and constructs a mathematical formulation, for example, in LaTeX code. It sends it back to the manager. If the manager thinks that's correct, it passes it on to the programmer, who turns the LaTeX code into code in a modeling language, for example, GuroBPy. If that's correct, the manager will pass that on to the evaluator, who runs the code on the given data and evaluates the solution. Okay. Based on that, the manager might decide to send it back to the formulator or send it back to the programmer, or it might decide the problem is solved and to output the solution. The pre-processing step is particularly important. In the pre-processing step, which is also powered by large language models, the description is parsed in order to identify a list of parameters with their dimensions and a definition of what that parameter is meant to represent. The objective of the problem, the goal, background on the problem, a list of constraints that appear in the problem, and a connection graph, which is initially null. I'll explain that in the next slide. As the formulator goes through the problem, each time it looks at the objective or one of the constraints, it evaluates which parameters are used by this constraint, and it adds those links between this constraint and those parameters to the formulation graph, and it identifies which variables are used in the constraint or whether any new variables need to be defined. Those are defined and then added to this graph. So now the nice thing about this is that we've identified this structure, which is that each constraint only depends on some parameters and some variables. So when we go to, for example, code that constraint, we don't need to look at the entire problem. We only need to look at those parameters and variables. This allows OptiMUS to scale to extremely long problem descriptions. Okay. So we should say there have been many other approaches to the problem, even though this field is very new. I think it's a field with a lot of people who are very excited. So there's been a lot of activity. I think I would say it sort of started in 2022 with a NeurIPS competition on natural language for optimization. And that also came with a benchmark data set, which has been very useful to us as we've developed OptiMUS. They also wrote a paper on sort of approaches to this problem, which were at the time not using large language models. I was also very inspired by this paper, LLMs as Optimizers, that was written by one of my former students who's now at Google, Chengrun Yang. And he thought of the LLMs, he was doing prompt optimization. He thought of them as optimizers. So we would say, here's a prompt, and here's the value, of what the solution the LLM returns. So for example, he has a traveling salesman problem and it's the length of the tour. He says, here's another prompt, and then here's the value of the solution it returned. He says, here are 4 examples of this. Now, please, large language model, come up with a prompt that will improve the value of the solution. So this is a super cool idea for prompt optimization, and it does also work for solving optimization problems, but it certainly can't provide any guarantees, okay? And it doesn't work for large or complex problems. You could also ask the large language model to write a solver from scratch. This was the approach that's used in this paper, Fun Search. Again, it works for kind of simple problems, but it doesn't leverage the amount of code, and the sophistication of the solver code that we have right now. So I think that using solvers as tools is probably going to be the way to go for a very long time, even as AI develops and gets better. A third approach is asking an LLM to call a solver. I think this is something that's used in the Chain of Experts paper, which was recently accepted into iClear. And they also use this idea of having multiple experts interact with and talk with each other. Then there have been several works on chatbots for optimization, including chatbots that can help you identify and fix infeasible problems, do what-if analysis for changing aspects of your problem and seeing what will change about the answer, or even a chatbot for helping you model these problems. But these haven't been sort of extensively tested on benchmarks, so there's not as much understanding of their capabilities and limitations. Okay, so let me tell you how the OptiMUS architecture does on these tasks. So there are three major data sets that we used for assessing how well these methods work for optimization modeling. One is NL for opt, which comes from this NeurIP competition. There are a lot of instances, which is great, but they're pretty short and they're very simple. A second one is a complex OR data set that was introduced in the Chain of Experts paper. The problems are still quite short, but they're a little bit more complex, including a couple of integer problems. And finally, there's our data set, which has problems that are much longer and more complex. Okay, and again, there's more of them compared to complex OR. Okay, so here's the figure of merit if this were a CS conference paper. So we've got these three different data sets. Okay, and if you just ask ChatGPT to write you solver code, to call the solver, it's able to solve almost 50% of the problems on the data set I told you is quite simple, but very few of the data sets in problems in complex OR, and in our data sets sort of in the middle. If you ask it, you do a little bit of prompt optimization with reflection, it does a little bit better. If you use Chain of Experts, it does a little bit better. If you use OptiMUS, it does substantially better, especially on these complex data sets. Okay, so I would say this is a substantial improvement on the state of the art. On the other hand, this is definitely not yet reliable, right? I wouldn't, use out of the box and trust something at 78%. If you told me a self-driving car was accurate 78% of the time, I would not get in that car, right? Okay, so there's still a lot of work to do, or possibly this is a lot of sort of scope for interaction. So it's worth understanding the kinds of mistakes it makes, and also how a human can sort of supervise and improve. Okay. We can also try OptiMUS with different large language models as backend. So here we sort of validate that using the top of the line, current large language model at the time that we wrote this was GPT-4. It's still approximately correct. I think Claude beats it, but not by much. It's right. Okay. So that's the table of numbers I told you before. If you don't do any debugging, the performance drops a little bit. If you use GPT 3.5 as the manager role, performance drops a little bit. If you try using GPT 3.5 as all of the roles, including the programmer and the formulator, the performance drops a lot. Okay. And if you try using the mixed role model, it almost can't solve any of the problems. Okay, so here we're seeing that using a good large language model is very important. And we expect that sort of the entire system will improve as the large language models improve. I also like this point that dumbing down the manager is okay, but dumbing down the individual contributors like the formulator, programmer, and evaluator really hurts performance. Yeah. Let's think about what happens as a function of the number of agent calls. So on the simplest data set, NL for opt, it doesn't matter if you allow them, as long as you call each agent once, you basically solve all the problems. You improve a little bit by allowing yourself to call one more agent or two more agents, but not much. Okay. On the other hand, on these more complex data sets, it is useful to call agents. And on NLP for LP, we observe improvements out to 8 agent calls. Okay. So there is actually a significant amount of sort of talking between agents, going back and correcting things. On the other hand, let's look at how it's using these agent calls. Among the problems that were solved, okay, basically the formulator is only called once. A couple of times it's called a little bit more than once, but basically once, right? So on the simple problems, you call formulator, then programmer, then evaluator, then you're done. Okay. On the complex problems, basically what you do is you go formulator, programmer, evaluator. Doesn't work, send it back to the programmer a second time, evaluator a second time, and then you're done. Okay. So that's the sort of stereotypical way that it would proceed through this system. I think one really interesting challenge is figuring out how to identify when the formulator is wrong and how to improve the formulation. That's something that I think is really an optimization specific task that would be difficult for a large language model that's not specifically looking at this task. When OptiMUS fails, what are the reasons? Sometimes it's incorrect modeling. Sometimes it's missing constraints. Sometimes it's coding errors. On these more complex data sets, coding errors are less likely to be the reason. Incorrect modeling tends to be really significant. Okay, I think it's kind of impressive. Missing constraints is not a substantial part of the reason. So OptiMUS is doing a good job of making sure to remember, identify, and keep track of all the constraints. Okay, so let me show you, if we're thinking about, how do we correct incorrect models or what kinds of mistakes does it make, it's much easier to see that in an interactive paradigm. So let me show you an interactive demo that my students built in order to assess and to work with this optimization modeling language. So here's our example problem that we'll be working with. It's a production planning problem. Okay. So I'll let you read it for a little bit, but it's pretty standard. By the way, the web app is accessible. Any of you can try it. You can just search for OptiMUS web app and you'll find it. It's also linked from our GitHub page and from our, I think also from our paper. Okay, the first step is you input the description like you saw on the previous slide, and then you ask it to pull out the parameters. And it will identify each of the parameters in problems. It says, a number of products, I'll call that P. Produced at a specific rate, I'll call that production rate. Okay, so it's introduced these variables for you and it's decided what to call them and which ones need to be, the parameters, which one need to be parameters, okay? So by doing this, it's identifying what problem data are you going to need to feed it for it to be able to solve the problem. Okay, these are all editable. So, for example, if it gets the dimension wrong, or if you just don't like the name of the parameter, or if it sort of subtly got the definition of what the parameter is meant to represent wrong, you can edit that. If something isn't a parameter, you can delete it. And if there's parameters that didn't identify, you can add them right here. Okay, next step is it looks at the description and tries to pull out what is the objective, what's the background on the problem, and what are the constraints. Okay, so here if we look through the constraints, right, so the objective of the company aims to maximize total profit from selling all products. That's correct. Okay, each product can only be produced in non-negative quantities. That's correct. The production volume for each product must be an integer if products cannot be fractionally produced. That's a weird constraint, right? Because it's like it's a little bit redundant. It's